You're looking at the most distant galaxy ever detected, over 13 billion light-years away. But here's what will mess with your head. If you could somehow travel there instantly, you wouldn't find the edge of the universe. You'd just see more galaxies stretching endlessly in every direction, with Earth now sitting on your new horizon. So what exactly would you see at the edge of the universe? The answer depends on which edge you're talking about. And there are at least 4 different ones. Let me start with something that sounds simple, but isn't. What do we mean by the universe? Because when most people ask about the edge of the universe, they're actually mixing up 2 completely different things. First, there's the universe, capital U, which is everything that exists. All of space, all of matter, all of energy, everywhere. This universe, as far as we can tell, might have no edge. It either goes on forever, or it might curve back on itself like the surface of a sphere, where you could travel in a straight line and eventually end up back where you started. Though we're not certain which scenario is correct. But then there's the observable universe, lowercase o, which is the bubble of space around Earth from which light has had time to reach us. This absolutely has an edge, and it's this edge that we can actually talk about seeing. Think of it like being on a ship in the middle of the ocean. There's a horizon and a clear line where the sky meets the water. You know there's more ocean beyond that horizon, but you can't see it because of the curvature of the Earth. The observable universe works the same way, except instead of Earth's curvature blocking your view, it's the finite age of the universe and the speed of light that create the horizon. The universe is about 13.8 billion years old. Light travels at 186,000 miles per second, fast but not infinitely fast. So there's a fundamental limit to how far back in time we can see. We can only observe light from events that happened after the universe became transparent to light, which was about 380,000 years after the Big Bang. But here's where it gets tricky. Space itself has been expanding this whole time. Imagine you're standing on a moving walkway at the airport, and someone at the far end throws you a ball. By the time the ball reaches you, that person has moved even farther away. The same thing happens with light in an expanding universe. A galaxy whose light has traveled for 13 billion years to reach us isn't 13 billion light-years away anymore. Due to cosmic expansion during that light's journey, that galaxy is now about 46 billion light-years away. So the edge of our observable universe is actually about 46 billion light-years in every direction, making the whole observable universe about 93 billion light-years across. So what would you actually see if you could somehow travel to this edge? Let's take an imaginary journey and watch how things change as we head toward the boundary of everything we can observe. Imagine you're in a spacecraft that can travel faster than light. Impossible, but stay with me. You start near Earth and begin flying outward in any direction. For the first few billion light-years, things look pretty familiar. You see galaxies that look a lot like the Milky Way, galaxy clusters that resemble our local neighborhood, the same types of stars and cosmic structures. But as you travel farther, something strange starts happening. The galaxies you're passing look younger, their stars are bluer and more massive. There are fewer heavy elements, less carbon, oxygen, silicon, because there hasn't been enough time for multiple generations of stars to live, die, and scatter these elements through space. By the time you've traveled 10 billion light-years from Earth, you're seeing the universe as it was 10 billion years ago. The galaxies are smaller, more chaotic. Many are in the process of colliding and merging. The whole cosmic web of matter looks less organized, more turbulent. Keep going. At 12 billion light-years out, galaxies are becoming more primitive. Many are actively forming their first generation of stars. The universe is denser, hotter. The cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space, is noticeably warmer at this earlier epoch. Now you're approaching 13 billion light-years from Earth. The galaxies are getting sparse. Many are just barely forming. You're seeing the universe in its cosmic dawn, when the first stars were igniting and beginning to light up the darkness. At the farthest distances we can observe, something dramatic happens. The first galaxies become increasingly rare and primitive. You're approaching what astronomers call the Dark Ages, a time before the first stars formed, when the universe was filled with nothing but hydrogen and helium gas, slowly collapsing under its own gravity, but not yet dense enough to ignite nuclear fusion. But you're not at the edge yet. Keep going, and at about 13.7 billion light-years from Earth, you encounter something remarkable, a wall of light. This is the cosmic microwave background, the farthest thing we can see in any direction. It's the afterglow of the moment, about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms for the first time. Before this moment, the universe was opaque, like being inside a thick fog. Photons couldn't travel very far before hitting an electron and scattering. But when atoms formed, the fog suddenly lifted and light could travel freely through space for the first time. That light has been traveling ever since, and it's what we see as the cosmic microwave background. This is as far as you can see with light. It's like a spherical wall surrounding the entire observable universe, glowing at a temperature of about 2.7 degrees above absolute zero. But here's the crucial part. This isn't actually an edge or a barrier, it's just the limit of how far back in time we can see using electromagnetic radiation. Now here's where our simple story gets complicated, and where most people, including some scientists, get confused about what the edge of the universe really means. First, that cosmic microwave background wall I just described. It's not sitting still. Every second that passes, light from slightly farther away has time to reach us. So the edge of the observable universe is constantly expanding outward at the speed of light. In 1 year, we can see about 1 light-year farther in every direction. But there's a catch. Remember, space itself is expanding. In some directions, space is expanding so fast that even though light is traveling toward us at maximum speed, it's actually getting farther away from us. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. This creates what cosmologists call the event horizon, a boundary beyond which we will never, ever be able to see, no matter how long we wait. Objects beyond this boundary are being carried away from us faster than their light can reach us. This horizon is currently about 16 billion light-years away, and, unlike the observable universe boundary, it's actually shrinking over time. So we have multiple edges, the edge of what we can see now, the edge of what we'll ever be able to see, and the edge of what we could theoretically reach if we started traveling today at the speed of light. But wait, there's more. Some cosmologists argue there might be other kinds of edges we haven't even detected yet. What if the universe has different physical laws in different regions? What if the fundamental constants, things like the strength of gravity or the speed of light, change as you travel far enough? We have no evidence for this, but it's theoretically possible. If you traveled far enough, you might encounter regions where matter behaves differently, where different types of particles exist, or where the very fabric of space-time has different properties. There's also the question of what happened before the cosmic microwave background. We can't see farther back with light, but maybe we could detect other signals. Gravitational waves, for instance, can travel through the opaque early universe. Future detectors might be able to see gravitational wave signatures from the very first moments after the Big Bang, effectively pushing back our observational edge even farther. And then there's the biggest complication of all. We don't actually know if the universe has a true edge. The most likely scenario, based on our best measurements, is that the universe is infinite. If you could somehow travel far enough in any direction, farther than the observable universe, farther than the event horizon, farther than any boundary we've discussed, you would just find more space, more galaxies, more cosmic structure, stretching on forever. But there's a small chance we're wrong. The universe might be finite but so large that we can't detect its curvature. In that case, there might be a true edge somewhere out there, a place where space itself ends. What would you find there? Nobody knows. It might be a boundary with some other realm, or it might be that the very concept of there breaks down at such a boundary. Why does any of this matter to you, sitting here on Earth, probably never planning to travel even to the nearest star, let alone to the edge of the observable universe? Because understanding these cosmic boundaries changes how you think about your place in existence itself. First, it puts the scale of reality into perspective. Every human who has ever lived, every civilization, every story, every triumph and tragedy in our entire history has taken place in a region of space so small that if the observable universe were the size of Earth, our entire galaxy would be smaller than a grain of sand. But here's what's really mind-bending. If the universe is infinite, then everything that's physically possible has happened somewhere. There are regions of space so distant that they're completely causally disconnected from us. Nothing that happens here can ever affect them, and nothing that happens there can ever affect us. In those regions, there might be exact copies of Earth, or versions where history unfolded differently. This also affects how we think about the future of our species. If we ever become a spacefaring civilization, there are fundamental limits to how far we can spread. Because of the expansion of space, there are galaxies that we could reach if we left today, but if we wait too long, they'll be carried beyond our reach forever. The window for intergalactic travel is slowly closing. On a more immediate level, understanding cosmic horizons helps you grasp why cosmology is such a challenging science. Unlike other fields where you can do experiments, cosmologists can only observe. And they're limited to seeing the universe from one location, Earth, at one moment in cosmic time. It's like trying to understand the entire ocean by examining a single drop of water. Yet from that single vantage point, we've managed to piece together the story of cosmic evolution, the formation of galaxies, the synthesis of elements, and the ultimate fate of everything. The edge of the observable universe isn't just a boundary, it's a time machine that lets us see the universe's history written across the sky. Every time you look up at the night sky, you're seeing different cosmic edges. The nearest stars show you the galaxy as it was a few years ago. Distant galaxies show you cosmic history from millions or billions of years ago. And if you could see the cosmic microwave background with your naked eye, you'd be looking at the universe as it was when it was less than 400,000 years old, long before Earth, the Sun, or even the Milky Way existed. So what would you see at the edge of the universe? The answer is, it depends on which edge you mean. At the edge of the observable universe, you'd see the cosmic microwave background, a faint glow from when the universe first became transparent. At the edge of what we'll ever be able to observe, you'd see galaxies being carried away by cosmic expansion faster than their light can reach us. And at the edge of the universe itself? Well, if our best theories are right, there is no edge, just more space, more galaxies, and more cosmic structure stretching on infinitely. The real edge isn't in space at all. It's in time. We're limited not by walls or boundaries, but by the finite age of the universe and the speed of light. The edge of everything we can know is painted across the sky every night, telling the story of cosmic evolution from the Big Bang to today. And every day that edge expands a little farther, revealing new chapters in the universe's biography.